This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com. The title of the lecture is Our Star, the Sun. The energy in the Sun is produced at its central core. This energy is in the form of electromagnetic radiation. If this energy had free run, it would have crossed the surface in 2 or 3 seconds. But that does not happen. In fact, this energy takes almost 10 to the power 5 to 10 to the power 6 years to cross the Sun. Why is it so? So in this lecture, we are going to understand the reason for this, and in the process we are going to learn some of the physics of the Sun. Let's get started. So here you see a picture of the Sun, surface of the Sun, taken by NASA, and what are these arch-like things we will address in this lecture. So before we go into the main topic, this is the Hertzsprung-Russell diagram. So what you see here is, this is my temperature axis. So this is the temperature axis, and the temperature increases in this direction. And this is the luminosity. Luminosity is energy emitted per unit area per unit time. So this is the direction of increase of the luminosity. So this is about stars. Our Sun is one of the stars, and all the stars burn hydrogen at their core. So this is a plot of luminosity versus temperature of the stars. So what we have here is, in this section, which is called the main sequence, this one, this is the main sequence. So in this belt, all the stars that are there are now alive. By alive, I mean the gravitational force of the Sun is balanced by the radiation pressure. So our Sun, this is where our Sun is situated in this graph. So here we have the bigger stars, and down here we have the smaller stars. So you can see the smaller stars have lower luminosity and a lower temperature, while the bigger stars have high luminosity and higher temperature. And here you can see a color coding. So the smaller stars are shown as red, and the bigger stars are shown as blue. That is, there is a shift in frequency as we go from the smaller stars to the bigger stars, and the frequency increases. So the temperature is also a marker of the color of the star. And once the star dies, it falls out of this main sequence. So the Sun here, it's going to become a white dwarf, so it will go somewhere here. And the bigger stars, they end up being neutron stars or black holes. So here you have one of the stars which is dying. This is Betelgeuse. So this is now this is existing as a red supergiant, and in the near future it's going to explode as supernova, and finally it may end up being a black hole. So we'll go to the next slide. This slide is about the Parker Solar Probe. This Parker Solar Probe was launched in 2019, and it is the most sophisticated solar probe that has been launched by NASA till date. The probe will come closer to the sun more than any other probe that has been launched till date. In fact, in 2024, the Parker Solar Probe will be around 7 million kilometers from the sun, and this is the rocket that launched the Parker Solar Probe in 2019. This is the Delta 4 heavy rocket. It has been retired since then. This rocket is not operational anymore. So next slide, we'll have a look at the Parker Solar Probe. So this is the Parker Solar Probe. The main feature of the Parker Solar Probe is its insulation. The insulation of Parker Solar Probe can withstand a temperature of 1300 degrees centigrade, and inside the probe where all the electronic instruments are located, the temperature is 20 degrees. The research on this material took NASA almost 20 years, but the outcome has been spectacular. So what does the probe do? So how does the solar probe the sun? What the solar probe does, one of the things it does is that it measures the various oscillations of the sun. It measures the various frequencies of the oscillation. The sun has characteristic oscillations, and these characteristic oscillations tell a lot about the sun. So once the frequencies have been measured, software can reconstruct the sun. This is the field of helioseismology. So we'll go to the next slide. Here we see the various layers of the sun. So at the center we have the core, which is the inner core, and just outside the center inner core we have the radiative zone. So this is an important zone. And why it's important? Like in the context of the lecture, this is a very important zone. Next we have the convection zone. Then we have the subsurface flows. Then we have the layer which is called the photosphere. Then we have the layer which is called the chromosphere, and finally we have the corona. So sun is not a homogeneous object. It has many layers, and these are the various layers of the sun. We now go to the next slide. Here the layers have been shown, but in a two-dimensional fashion. So the central layer, which is denoted by 1 here, is the inner core. 2 denotes the radiative layer. 3 denotes the convective layer. 4 denotes the photosphere. 5 denotes the chromosphere, and 6 denotes the corona. You can see for corona there is only a lower edge. There is no outer edge for the corona. And for all other layers you have like here you have all one inner edge and one outer edge. So we go to the inner core first. So we are going to study all the cores, and the energy is produced in the inner core. Then it crosses all these layers, and finally it comes out of the sun. This takes almost 10 to the power 5 to 10 to the power 6 years, and we are going to see the reason for this. So we are going to go to the next slide. The inner core is characterized by extremely high temperature. The temperature is around, you can see the temperature is extremely high. This is 1.5 into 10 to the power 7 Kelvin. And how did we like get such high temperature? We should remember the sun was born in a nebula, and as the dust in the nebula contracted under gravitational force, the gravitational energy was converted into enormous thermal energy, and that is how we get the core to be so hot. And when the core gets so hot, nuclear reactions are initiated, and this energy is produced by the proton-proton cycle in the core. And we are going to see what is this proton-proton cycle that produces the energy, and that energy finally escapes the sun and reaches us. A part of it reaches us. So we'll go to the next slide. So in this slide we are going to see the proton-proton cycle which powers the sun. So here we have, so 1H1, this is the proton, this is the proton. So two protons fuse together because of this high temperature, this reaction is taking place, fuse together to form a deuterium, and you have positron, you have neutrino, and you have kinetic energy. It doesn't stop there. Then this proton and deuterium, they again fuse to form helium-3, and then you have the photon. This is the gamma photon. So this is the gamma photon. So this is the energy that will finally come out of the sun. So this gamma photon has extremely high energy. And then this proton again combines with this helium-3 nucleus and forms helium-4 nucleus, and then we have positron, and then we have neutrino, and it ends with the two helium-3 nuclei combining to form helium-4 and protons. This is my proton-proton cycle, and this is the cycle. So these are the nuclear reactions that power the sun, and this is the gamma photon that is eventually released by the sun. And we will see how this photon travels. So in the next slide, we'll be in the next zone, which is the radiative zone, and the radiative zone is diffusive in nature. So we'll understand what diffusion is. So in the radiative zone, you can see the temperature is between 10 to the power 2 into 10 to the power 6 Kelvin and 10 to the power 7 into 10 to the power 6 Kelvin. So in this radiative zone, the temperature has come down sufficiently so that the nuclear reactions are stopped. So this temperature cannot sustain nuclear reaction. To sustain nuclear reaction, we have to go to higher temperature. So power production or energy production has stopped in the radiative zone. So what happens in the radiative zone? The radiative zone is very, very hot. So it's a soup of ionized gases, hydrogen, helium, and electrons. The energy in this radiative zone is transferred through radiative diffusion. We'll explain this radiative diffusion in the next few slides. So, what is diffusion? So, in order to understand diffusion, we will discuss something called random walk. So this is say x-axis, this is x-axis, and suppose someone starts at the point 0. This is x-axis, and you have points which are denoted by 1, 2, 3, 4, 5, 6 on the right hand side, and on the left hand side we have points like -1, -2, -3, and so on and so forth. So suppose a person starts from here, and then the person can go either to the right with probability p, or the person can go to the left with probability 1 minus p. For sake of simplicity, we will take the probability to be half. It doesn't change the physics. So if from 0 to the person goes to 1, again from 1 it can either go to 2, or it can again come back to 1. It can go to 2 with probability p, and it can come back to 0 with probability 1 minus p. So this kind of walk proceeds like this. So it's a random walk. And so if the person takes n steps, if the person takes n steps, then how many such possibilities are there? How many such paths can be there? There can be 2 to the power n paths. Right? So if he starts from 0, it can go this way or this way, 2 ways. And once it reaches 1, it can either go right or left. So that will be 2. So if it takes n steps, then there will be 2 to the power n distinct paths. So what one can do is one can calculate the average over these 2 to the power n paths. So we do x average over these 2 to the power n parts. And what is x? X is x is 0. So average of x is 0. So x is the distance traveled from 0. X is the distance traveled from 0. So x can be positive or negative. If it goes to the right, it's positive. If it goes to the left, it's negative. So you can clearly see if p is half, x is 0. So the average, so x can be both positive and negative with equal probability. So it's 0. But if you take x square, then what happens? If you take the average of x square over these 2 to the power n parts, then what we see that this x square goes as n. So what it tells us that the particle does not remain confined around 0, but it surely moves away from this 0. Either it goes to the right or it goes to the left, and as the number of steps increase, it moves further and further away from 0. And how it goes away? It is defined by this expression. It goes as n. Now there is no time involved here, so we have not introduced any time, but we can introduce time in this problem by introducing, so here we had introduced a probability of going from this side to this side, p. But instead of that, if we introduce a probability per unit time of going from 0 to 1, 1 to 2, or 0 to -1, then we can introduce time into this problem. And once we introduce this time into this problem through this probability per unit time, then what do we get? That we will see in this next slide. So in this slide, we are going to discuss the simple diffusion equation. As I told you, if we introduce time into this problem, then what we get is a very fundamental equation in physics which represents simple diffusion equation. So this is the simple diffusion equation. This is the differential equation. Here I have written it in one-dimensional form. So P is the probability of finding the person at position x at time t. And this probability follows a differential equation which is the simple diffusion equation, and this d is a constant and d is called the diffusion constant. Here I am presenting a very simplistic picture of diffusion. So this is the most simple form of diffusion you can have. You can have more complicated forms of diffusion which we are not going into. So what my idea here is, I am going to show here that the process of diffusion is a very slow process. So we are in the radiative zone, and the radiative zone, the energy is transported through diffusion, and since it is transported by diffusion, it's going to be a very slow process. So that is what we are going to see. So what we see here is the diffusion equation I have written, but I have written in 3D form. So this is not important. We have written x, but x here represents x, y and z. Here also x represents x, y and z. Here also x represents x, y and z. Now the important thing that we can deduce here is that the dimension, so the dimension of this diffusion constant d is clearly, you can see from here, if p is from here, you can see that the dimension is the dimension of L square by t. T is the time. This is the dimension of the diffusion constant. So the diffusion constant, if it goes to 0, that means there is hardly any diffusion, or the diffusion is very slow. And if the diffusion constant is a high number, then we can say that the diffusion is very rapid. Now we know what is the dimension of d. We can now construct a time scale from the dimension of d. So what does it mean? Suppose I am interested in how much time on an average it will take for a person or a particle to go a distance L. So this is L through the process of diffusion. So we can say that the time that it requires goes as L square by d. You can see this has the dimension of time. This has the dimension of time. So what is the significance of this? So the significance of this is, so you can see that if L is increased 2 folds, then the time to cross the distance L also increases 4 folds, right? But if you consider directed motion, like a motion that is happening with a definite velocity v, then the time taken for it to travel a distance L is L by v. Okay, so here the time scales as L, whereas here the time scales as L square. So that's what makes the process very slow, the process of diffusion. At the same time, if the diffusion constant d is very small, then this time scale also becomes very large. So if it's a very slow process, if the diffusion is very slow, obviously the time scale becomes very large, and that is what happens in this radiative zone. So we'll now go to the next slide. What happens in the radiative zone? Absorption and emission of photon. So what happens is that once the gamma photon which has been produced in the core of the sun crosses over to the radiative zone, it may be absorbed by an electron. So electron is a charged particle and the gamma photon is represents the electromagnetic field. So it's natural that the electron will interact with the gamma photon, and in the process what happens, it may get excited and go to a higher level. So this is the excitation of electron, and the same electron may get de-excited by emitting a gamma photon or another photon of slightly lower energy, which may be an X-ray photon, and it may come back to a lower energy level. Now, the thing that we have to remember here is that the emitted photon is emitted in a random direction. So it can be emitted in this direction, or it can be emitted in this direction, or it can be emitted in this direction with some probability. So this is something very similar to the situation in random walk or diffusion. So because of this random nature of emission, the progress of energy transport is severely obstructed. And so what we are seeing is this is a kind of diffusion that is taking place, and that is why the transport of energy is slowed down in the radiative zone. We'll now go to the next slide. So in the next slide, we are now in a different zone. So core covered, then radiative zone covered. Now we are in the convection zone. So before we understand the convection zone, what is convection, and before that, what is conduction? So you have two plates here. One is having a higher temperature and at temperature TL, and another plate which is lower temperature TU. And the difference between the temperature of the two plates is delta T, and the distance between the two plates is H. And suppose we are on the surface of the earth. It's not required here for this conduction thing. And so the heat flows from heat flows from the lower plate to the upper plate, but there is no material motion of the medium. So if the medium is a fluid, then there is no macroscopic motion of the fluid. The heat transfers through microscopic motion. That is conduction. Conduction is a kind of diffusive process. We will see that soon. So this is conduction. So what is convection? That we are going to see in the next few slides. So what is convection? The geometry is the same. Suppose we are on the surface of the earth. Now what happens is that if the temperature delta T I keep on increasing, then what we will see is that the macroscopic motion of the fluid sets in. And what we get is these kind of rolls. So what we are getting is this kind of rolls. The fluid is moving in such rolls. Here also similar thing. So fluid is coming down, going up, coming up, going down. This is convection. And in the next slide we will study it in greater details. So this kind of convection is called Rayleigh-Bénard convection on the surface of the earth. So this buoyancy plays an important part. So what happens is, so this is a typical setup, and this plate is say at a high temperature, and here it is at a low temperature. And so what happens, that the hot fluid, it expands and it rises up. Okay, so gravity plays an important part in this role. So on the surface of the earth we consider G to be constant, so it rises up, and then when it reaches the upper part is cool, so it gradually cools down, and then as it cools down it becomes heavier and it sinks. So this motion keeps continuing. Here also the same thing. The hot liquid rises up and then the cold liquid falls. So these are convective cells. So what we are having, this is a cell, this is a cell. So that is how the convection takes place. So in the next slide we'll learn more about convection. So onset of convection. So why does convection start? Initially, if the temperature difference is very small, what we have is diffusion. The temperature of the fluid is marked by a diffusive process. This is the typical diffusion equation that we have encountered before, isn't it? This is the diffusion equation that we have encountered before. So the temperature satisfies the diffusion equation, and this is a kind of diffusive constant. But initially, the temperature is clearly governed by the diffusive equation. But what happens if the temperature is raised? So if delta T is raised, the difference in temperature of the upper plate and lower plate, then some kind of instability, there is some kind of instability in the fluid, and that results in convection. For convection there is a very important dimensionless number. That number is the Rayleigh number. So convection is determined by the Rayleigh number. So Rayleigh number, it depends on delta T, it depends on H, the distance between the plates, and then you have depends on the viscosity, and it depends on the diffusive constant chi. So why is it important? So in the next point we'll see. So convection sets in when our Rayleigh number is greater than some critical value. So for liquid on the surface of the earth, the critical value will be, I think is, I don't remember the exact number, but it will be somewhere around 1000. A little more than 1000, maybe 1200 or so. So if the Rayleigh number is less than 1000, then you can be assured that only conduction is taking place. But if the Rayleigh number exceeds 1000, then both conduction and convection are there. But as the Rayleigh number keeps increasing, the conduction is suppressed and convection takes over. So you can tune the Rayleigh number by viscosity. So if the fluid is less viscous, then this nu is small, then the Rayleigh number increases. Or I can increase the Rayleigh number by increasing the temperature difference. Or I can increase the Rayleigh number by changing the diffusive constant. So this is convection. So this is convection on the surface of the earth. But convection is a phenomena of fluid dynamics. So if its convection is there on the surface of the earth, then convection will be there in any fluid on any other planet or star. So we go to the next slide. Now, in the convective zone, what we see is that the temperature, the lower edge of the convective zone has a temperature of 2 into 10 to the power 6 Kelvin, and the upper edge has a temperature of 6000 Kelvin. So you can see that the temperature across the convective zone falls very sharply. So the convection carries the energy from the inner layer to the outer layer. Now in sun convection is taking place because the plasma in the convective zone acts as some kind of fluid. That's why we are having convection. So in the next, so this is magnetohydrodynamics. So we are still in the convective zone. So if you are in the convective zone, then we should remember that this is the Navier-Stokes equation. So this is the equation that governs fluid dynamics. So this is like Newton's equation. This part is the inertial term, that for a single particle you write m into dv dt, and on the right hand side is the force term. So the force term consists of pressure gradient, then you have viscous force, this is the viscosity term, and then you have the external force. So this is the external force. So this is for a single particle. So this is the external force. So the external, so when you're doing magnetohydrodynamics, we need Navier-Stokes equation, and then we remember, and we need the Maxwell's equation. Here I have written only one Maxwell's equation, there are four, right? So magnetohydrodynamics is very complicated. So this is the fluid dynamics of plasma. So in order to understand the fluid dynamics of plasma, we need Navier-Stokes equation, and we need the Maxwell's equations, and this force can be, this force can be the Lorentz force. So part of it is Lorentz force. So what is Lorentz force? This is the Lorentz force. For a single charge, we write the Lorentz force as Q into V cross B plus E. But if you go to continuum, then the Lorentz force can be written as current density cross B plus charge density times E. So J is the current density. So this is my Lorentz force for in fluid plasma. And when we are talking about convection, we cannot ignore the gravitational force. So what we have is, here you can add one more term, that is the acceleration due to gravity due to the sun, g sun, and this is a complicated term. This will not be a constant like it is on the surface of the earth, right? So you have to solve this equation, and this equation cannot be solved analytically. You have to go to a computer and you have to make several simplifications, etc., etc. So we will not go there. This just to give you a flavor about what is happening. So we'll go to the next slide and summarize everything. So now we will summarize what's happening in the radiative zone and in the convective zone. So here in this diagram we have, along this we have the radius is plotted along this, so radius of the sun, and here we have plotted the density. So this is the density. Okay, so you can see that, so here you can see that, inside the core, matter is extremely dense, and when you go to the radiative zone, you can see that at the lower edge of the dense radiative zone, you have a density of 10,000 kg per meter cubed. This is like the density of lead. So matter is so dense. So if in that dense matter you have diffusion, you can as well understand how low the diffusive constant will be. And as you cross the radiative zone, the density decreases. So, and when you are like close to the outer edge of the convective zone, the density is around 100 kg per meter cubed. And now we are in the convective zone. So the lower edge of the convective zone is around, the density is around 100 kg per meter cubed. You can here see, and then at the upper edge, the density drops sharply, and it is now 10 kg per meter cubed, because the outer edge is quite cool compared to the lower edge. So what you see is that the radiation crosses the inner core, then it is in the radiative zone, so it performs lot of zigzags because of the diffusive process. So here it is stuck for a long time, and eventually it will leave this zone, but it takes 10 to the power 5 years, almost 10 to the power 5 years or more for it to cross this zone. And once it crosses this zone, it is into the convective zone. And for convective zone, the process is very fast. It may take some 4 to 5 weeks for it to cross the convective zone. So here itself it takes all the time, 10 to the power 5 or more years, and here it will be of the order of few weeks, and it's here. The energy has reached this edge. Now we go to the next slide. So in this slide what we see is that we are now into the photosphere. So we have crossed the convective zone and we are now into the photosphere. The photosphere is a very thin zone. It's like few hundred kilometers thick, that's it. But this photosphere is important in the sense that this is where the plasma cools so much that it emits radiation in the visible region. So the temperature in the photosphere lies between, so the lower edge of the photosphere has a temperature of 6500 degree Kelvin and the upper edge has a temperature of 4000 Kelvin. So because of this low temperature and the nature of the plasma, the emission is in the visible region, and that is when we see the sun. We see the sun because of photosphere. Below, whatever is there below the photosphere is opaque to us, because whatever radiation is coming out from that zone, it's not in the visible region, never. So because of photosphere we see the sun, and what we see in the photosphere are granular regions. So what are the granular regions? We will see in the next slide. And another important feature of photosphere is the appearance of sunspots. So whatever you just see the granular regions, you see the small dark regions surrounded by black regions. These are all convection cells. So if you're looking at the top, what you are seeing is the bright spots represent the rising hot plasma, and the black regions represent the sinking or the plasma that is the cool plasma that is going down, and that is why it appears black. So the surface of the sun has a mosaic of these cells. And if you, this is a top view, and if you if you go inside and have a transverse view, the picture is quite clear. So this is the top, and this is what happening is that the hot gas or plasma is rising, and it cools down, and it again comes down at the edges. Here also the same thing is happening. So we'll go to the next slide now. We will now discuss sunspots. So what you are seeing here, these are all sunspots. And sunspots come in pairs. We'll discuss that, why they come in pairs, and they are regions of intense magnetic field. How high the magnetic field can be, that also we will see in the next few slides. So sunspots, so these are the sunspots on the sun. So these appear as black spots, but if you zoom in on a sunspot, you're going to see that it has finer structure. So there is a black region. The black region is called umbra. So every sunspot has an umbra, and there is one adjoining region which is not so black. This is the penumbra. And the black region is actually not black. What's happening is that the radiation in the black region is mostly out of the visible region. This is so because the temperature at the sunspot will be around 1000 degree Kelvin lower than the adjoining region, which appears as bright in this diagram. So if the adjoining region is say around 5000 or 4000 Kelvin, the sunspots will be at say 3000 Kelvin, and that's why they appear black. So these sunspots can be seen on the photosphere. We'll go to the next slide and see what are the characteristics of sunspot. Why do we have sunspots? Sunspots come in pairs, and here you can see two sunspots. From one, magnetic field is emerging, and there is another sunspot in which the lines are emerging, and the lines are going into another sunspot. So you can see here, so this is the sunspot from where you have magnetic lines of force or magnetic field is emerging, and this is the sunspot into which the lines are going in. And these magnetic fields are very strong. They are so strong that they can support plasma. Why is it so? Because if the field is very strong, because of Lorentz force, the field can hold the plasma in very tight circles. So, and that is why we have these kind of arch-like structures across sunspots. And these structures are called solar prominence. So we saw in the very first slide this picture from NASA where we clearly saw one solar prominence. So that's the reason for solar prominence, because they are accompanied by a very strong magnetic field, and hence they support the plasma. So we go to the next slide. So now we discuss the characteristics of sunspots. Sunspots are not really some very local events. They're manifestations of something very big. They're related to a 11-year solar cycle. So what happens is that the sun flips its magnetic polarity every 11 years, and after 22 years its polarity is restored. So in this 11 year, there will be periods in which the frequency of sunspots will increase dramatically, and there will be periods in which the sunspot, the frequency of sunspots will be very low. And why this 11-year solar cycle happens? By the way, this Earth also has a magnetic field, and the magnetic polarity of the Earth also flips, but that takes tens and thousands of years. It's not that polarity flips in 11 years or 100 years or 200 years. It's not like that. So we'll see the solar cycle is related to the differential rotation of the Earth, of the Sun. Sorry. So the Sun is not a solid object, so it rotates differently at different positions. So at the equator, the Sun rotates very fast, so it can complete one rotation in say 20 days. Whereas near the poles, the rotation is very slow. So that takes say maybe around 30 days. So because of this, what happens is that the magnetic fields get distorted. Why magnetic fields get distorted? Because the plasma is a good conductor, and since plasma is a good conductor, the magnetic fields are pinned to the plasma. They follow the plasma faithfully, and as a result, the magnetic field gets stretched, distorted, lot of things happen, and that is why at some places and at certain periods of time we get the sunspots. And the characteristic feature of sunspots is very high magnetic field and solar prominence. So what do I mean by high magnetic field? How high? So at the sunspot, the magnetic field can be of the order of 10 to the power -1 Tesla. While in the adjoining region, the magnetic field will be around 10 to the power -4 Tesla. Typically, these are not exact numbers, they can vary. And when you compare all these things to the magnetic field on the surface of the Earth, the magnetic field on the surface of the Earth will be around 10 to the power -6 Tesla. So this magnetic field is very strong. And because of this strong magnetic field, we have solar prominence. It can really support the plasma, means it can overcome the gravitational pull on the plasma, this high magnetic field. And another thing about sunspot is that the sunspots they're not permanent features. They are very temporary features. So they can be there for a few hours or few days, and then they disappear. Okay, so then they disappear, and they also come in various sizes. So some sunspots can be quite small, and some of the sunspots can be as big as the Earth or even larger. And what happens at the sunspot? Why is the sunspot cool compared to the adjoining region? Is that because of this high magnetic field, the convective process is disrupted. Convection is a very good the convection is a very good method of transferring energy from the lower edge to the upper edge. But if this process is disrupted, then the energy transfer is also disrupted. So this energy is not transferred that efficiently to the upper edge. That's why the sunspot region remains comparatively cooler than the adjoining region. And another important feature of sunspot, what we say, it's a vortex. What is a vortex? we'll see it in the next slide, what is a vortex, and then we will also see what are solar flares. So we go to the. So now, what is a vortex? So we'll be considering spin vortex. So spin vortex means all the spins or magnetic moment. So spins can be attributed to electrons mm, or any charged particle. Okay, let's consider electrons. So suppose these are electrons and these are spins of the electrons, and right now they are frozen in space. So, and you can see the spins align themselves in a particular circle. Okay, so if you go around the circle, the spins eventually, when you come back to the same point, the spin aligns with itself. Now if you go inside a little, then the circumference of this circle becomes smaller, and again the spin has a shorter distance in which it has to align with itself. So if as it keeps going down, the distance becomes shorter and shorter till when it reaches the center, the spin has no scope to change and align with itself, and that is where this is a singularity and the spin can point up. So here we are talking of frozen spins. So now we can see in the sun, what happens is that the spins are not static, but they are circling round and round at extremely high velocity, and sometimes the velocity can exceed the speed of sound. So these spins are swirling around, and that's what makes a vortex. This is somewhat like, you can compare it to a tornado. So depending on the direction in which the spin changes, you can have a plus vortex, or a negative minus vortex. Thing is that, so the magnetic field comes out from the plus vortex and it enters the minus vortex, and these plus and minus vortices generally appear in pair, because if they appear in pair, it minimizes the energy. That's why you see the sunspots appearing in pairs. Now we'll go to the next slide. So now we'll discuss solar flares. So why do we have solar flares? Remember, the magnetic field at the sunspot is very high, and we know that the magnetic energy density goes as B square. The magnetic energy density goes as B square. What is the magnetic energy? Magnetic energy is the energy that is required to develop the current which is responsible for the magnetic field. So is the work done to develop the current which creates the magnetic field. So the work done is stored in the magnetic field, and this magnetic field is very strong. So what happens is, if the magnetic field snaps, because the magnetic field is under lot of stress, at some point the sunspots are not permanent features. When the magnetic field snaps, what happens is that this energy is released. The energy that is stored in the magnetic field is released, and it is released as the kinetic energy of the plasma, and that is when the plasma is thrown out into the sky, never to come back to the surface. So here we have pictures of solar flares, and one important thing to note is that the solar flares are not visible to naked eye. They emit radiation in ultraviolet and the X-ray region. So here you can see these photographs have been taken using UV cameras and X-ray cameras. So here you can see this one. This one is this one has used UV camera. This one has used UV camera. This is in the hard UV region. This is almost in the X-ray region. So you can see that the solar flares emit uh, very energetic, very high energy radiations, and they are mostly in the UV and the X-ray domain. We now come to the next slide. Now we are in the chromosphere. So from photosphere we are now in the chromosphere. So chromosphere, the lower edge of the chromosphere is at 4000 Kelvin, while the upper edge surprisingly is at 8000 Kelvin. This is remarkable because temperature increases output. This is very counterintuitive. The reason for this is not very well known, and that's why we have probes like Parker Solar Probe up there trying to take measurements and make sense out of things. So we now go to the next point. One thing is that the chromosphere appears red. And why does it appear red? Because of this H alpha line. H alpha line is an electronic transition in the hydrogen atom. Since the temperature is not very high, you will have some hydrogen atoms. And in those hydrogen atoms, this n is equal to 3 to n is equal to 2 transition takes place, which is a line in the Balmer series, I think. And because the frequency is red, that's why the chromosphere appears as red. And how do we know that? We'll go to the next slide and see. This is the chromosphere. So this is like during eclipse, you can, if you use a suitable camera, you can see this red tinge around the rim. So this is the light from the chromosphere, red light, corresponding to the H alpha line. And now we go to the corona. Corona has no upper boundary, and the lower edge of the corona has a temperature of around 2 into 10 to the power 6. This is again a very surprising. This is again, we don't know the reason exactly. The temperature increases drastically just above the chromosphere edge. And another important feature of this is, of course, the material has to be in plasma form or ionized form at such high temperature. And if corona is visible in green emission line, and X-rays you can understand, but why green emission? So this thing baffled scientists or experimentalists for a long time. This green emission, from where this green emission line is coming. So let's go to the next. So this is the corona, and what we see is the green emission in the corona. So scientists didn't understand because the frequency of this line or the wavelength of this line did not match any wavelength that they had observed in the laboratory on the surface of the Earth. So for a long time they wondered what this transition will be. And finally they figured out it is due to an iron ion. So you have iron there in the corona region, and it's in ionized form, and some electronic transition is taking place in an ion, and because of that this green light is forming. You are seeing this green light. So next slide is, So what about the spectrum of the light that is coming from the sun? Is it a black body spectrum? This is a black body spectrum. We know a black body absorbs all kinds of, so a black body absorbs radiation extremely well and it emits radiation extremely well. So what we have here is here, this is your wavelength increasing, that is the frequency decreasing, and here you have watt per square centimeter. This is the radiation from a black body. So here you can see at so this is at for a black body at 6000 degree Kelvin, the peak is around 500, it will be an angstrom, yeah, so 500 angstrom. So it's a visible region for a black body. So here for 5000 Kelvin also it's shown the peak will be more towards 6000 angstrom, and as we lower the temperature, the peak shifts to a higher wavelength. This is typically black body radiation. So what about the sun? What do we get from the sun? So that we'll see in the next slide. And this is the solar spectrum. So along the x-axis we have the wavelength. This is a log plot, and here also it is the intensity. So it's watt per meter square, but this is a log plot. So this is a log plot, and if we had a black body kind of radiation, then it would have looked like this. But it doesn't look like this. Only for the radiation which can be attributed to the photosphere, it looks like black body. Then from here it deviates, and that's because of the radiation from chromosphere and corona. So here we go to lower wavelengths, and lower wavelength means higher frequency. So from chromosphere we are having radiation at higher frequencies or lower wavelengths, and from corona also we are having radiation from very lower wavelength or very high frequencies. So this is the spectrum that we observe from sun. So sun is not a black body, right? So with this this lecture comes to an end, and thank you for your attention.